I'll let you introduce yourself. Welcome.
Great, thank you. It's a pleasure to be here this morning. Good to see you all. So, like I said, my name's Adrian Colyer. I'm actually a venture partner with Accel here in London, a venture capital firm. So it's actually my job to help find and build great technology companies in Europe. And prior to that, I worked in CTO roles with Pivotal, with VMware, with SpringSource, where I was the CTO for many years. As Marco said, though, the reason I'm here today is that I also write a blog, which is called The Morning Paper. You'll find it at blog.acolyer.org. I have this strange habit, strange to many people, of reviewing a computer science research paper pretty much every weekday and posting a summary of that paper on the blog. I've been doing this for just over 2 years now, so there's about 400 plus paper write-ups on the blog. And what I thought I'd do is just kind of look back and think through some of those papers, some of that research, and find the ones that really spoke to me about operational issues and share some of that research with you. My initial impression actually was that not many of the papers I read really say very much about operability. But when I look back, I was surprised just how many, although they didn't directly speak on the topic, though some do, had important wisdom to share with us that would shed some light on this topic. So my plan for the next 25 minutes or so is to share some of those papers with you. It'll be quite a whirlwind tour. Hopefully inspire you to dig deeper. I have got, at the end of the presentation, all the links to all the papers I'm going to talk about. I will post that on my Twitter account, etc. So don't worry about trying to scribble everything down if something catches your interest. OK, so the first theme that really struck me when I was sort of looking back through all these papers was this one. I think it rings very true for me, is that we can talk about operability, but actually an operable system and everything that's involved in that really starts with what you do in design and development. And if there was just one paper that I could share with you this morning, it would be this one, which is on designing and deploying internet scale services. It's by a guy called James Hamilton, who you may have heard of, written in 2007. And what's amazing about 2007 is that that's actually quite a long time ago, like 9 years, and it's packed with good advice, absolutely packed with good advice. I could easily spend my full half an hour talking to you just about this one paper, although that would really not be quite in the spirit of things. But one of the things that James says in this paper, and it rings very true for me, is we've long believed that at least 80% of operational issues actually originate in design and development. And so when a system actually does fail, yes, it's natural to look to operations, like what's going on, because that's where the problem is occurring, right in here and now. But most operational issues either have their genesis in design and development or are best solved there. And when you think about it, that's quite a powerful argument for DevOps being made way back in 2007 and the bringing together of the development and the operational perspective. There's another really interesting thing that James says in this paper related to this need to pull together service teams that have a shared responsibility. And this really rings true for me from my experience. I thought it was a wonderful quote. And he goes like this: if you call out the development if the development team is called out in the middle of the night when things go wrong, what tends to happen is that you get more automation. However, and I've definitely seen this, I'm sure some of you have, if the operations team gets called out in the middle of the night, the usual reaction is to grow the operations team. In other words, not to fix the root cause of the problem. And so in this paper, there are, in actual fact, I counted them, 76 different pieces of advice that James gives for how you would build an operable and scalable internet service. And it's quite interesting that he distills that into 3 things that you just have to remember. If you can't remember all 76, distill it down to 3. What are they? Now, these are pretty well known by now, but I think it's interesting to see that these were said back in 2007 and have really stood the test of time. So if you want to remember 3 things, number 1 is expect failures to happen and handle them gracefully. Number 2, keep things as simple as possible. There's enough complexity in the system as it is. And number 3, automate everything. You know, it's interesting when I wrote this paper up and I shared it on the blog, Adrian Cockcroft and Colton Andrus and a few other folks all got in touch and said, yeah, this is the paper we all studied at Netflix when we were starting to figure out how to design our systems. And several other groups came to me with similar kind of reactions. And so there's so much good advice in this paper that one of the things I did, and I'll post the link, is I took it all and I made it into an internet scale services checklist, which is just a gist on my GitHub account. that goes through all the things that he recommends that you do or have in place and think about. So there's plenty of them, but there's a checklist there that may be of use to you. Okay, so we can't spend all our time on those 76 points. As you can see, that might take a while. So let's look at some other things that might pique your interest. One of the themes that struck me was the question of sort of, how do I call it, figuring out what the hell's going on. So you've got a large-scale system, many moving parts, you're into microservices, whatever it is. How do you uncover the big picture, the dependencies between your components, the way that requests are flowing through the system, and sort of make sense of that and understand it? If you think about continuous deployment, etc., a static view of the system really isn't much use to you. It's always changing. So how do you deal with that? And one of the classic papers in this space is Google's Dapper paper, which is 2010. And they talk about the system they built called Dapper, their large-scale tracing infrastructure that actually injects tracing into pretty much everything that's going on in the Google system and captures samples of those traces, stores them in a database, and then they build a querying API on top so you can ask questions about what on earth is going on. I took away 3 key lessons from this paper. So the first lesson, and I've just touched on it really, is, look, when you reach a certain number of moving parts, this idea that there's a central configuration file that kind of describes exactly what happens in the system really doesn't hold anymore. And so you actually need to infer what the system of the structure of the system is at any point in time from what's really happening. And this is the quote from the paper. Modern internet services are often implemented in these complex large-scale systems made from lots of different software modules, built by lots of different teams, maybe using lots of different languages, etc. Understanding your system behavior in that context requires observations, observing related activities across many different programs and machines. So this is the first lesson. You can't really do it from a centralized file. You've got to observe and infer it. The second interesting lesson that I took away was that even your very best engineers actually aren't very good at guessing and intuiting what the cause of a problem is in this kind of environment. So when you've got lots of different subsystems or services, lots of different teams responsible for them, so even our best and most experienced engineers routinely guess wrong about the root cause of poor end-to-end performance. It's a tricky problem. And in that kind of situation, a system like Dapper that's actually got the facts recorded that you can go and query and probe, etc., is really important and help the team in Google to answer many important performance questions. Now, the third lesson in the paper was that, look, if you rely on your developers to go put in accurate and up-to-date tracing information in all of their code all over the place, it's going to go wrong. It'll be out of date, it'll be broken, it'll be incomplete, which is a phenomenon I also observed during my time as the lead of AspectJ and studying a number of systems doing this kind of thing. And so it's very hard to have your developers actually give you the accurate information that you need. So what do you do? How do you solve that? Well, the way that Google solved it is that they have a smallish number of shared components that everybody just uses. And so they can instrument those, and then you get what you need. But many people's worlds don't look like that. They're more diverse, including Facebook's. So Facebook have this problem, and they have a paper called The Mystery Machine that describes how they do end-to-end performance analysis of their services. Maybe this sort of captures some of what your systems look like. Many systems are like the Facebook ones. They grow over time. They favor innovation over standardization. They've got broad diversity of languages, middleware, execution environments, etc. Their view was, look, going back and adding instrumentation retrospectively to this smorgasbord of stuff we've got just isn't going to work. That's too big a task. We can't really practically do it. But we still need this kind of functionality we just talked about, so how do we get it? And their answer is this system called the Mystery Machine. And the basic idea is, well, we may not have this great trace, but don't worry, we've got logs. And boy, have we got a lot of logs from all these systems. And so maybe we can actually do something with the logs and infer causal structure. So look, our key observation is we've got a hell of a lot of logs, and we can gather information from that. And in particular, in the Facebook world, they say, well, in our log messages, we need a request identifier, which is the sneaky thing, because that has to go across the tiers so you can do the correlation. A host identifier for the host that produced the message, a host local timestamp, some unique event label. Give me that, and I can do causal analysis across all the logs, pull them into one place, The system's actually called UberTrace, which kind of makes me smile. And again, they sample, they don't keep everything, and they analyze it, and they put an API on top of it. And they're able to do causal analysis, and so uses the traces that have been generated and stored in this UberTrace system. So when I say causal model, it's like this component called that component, which called these three components, and understand the tree, etc. Looking at individual requests as they flow through Facebook systems. Based on that, they do a number of different types of performance analyses. First one is straightforward, show me the critical path, as you might expect. The next thing they do is looking at what we call the slack time in paths that aren't on the critical path. So how much leeway do I have? How many milliseconds play do I have before this becomes the critical path? The reason that's interesting is that when you're scheduling, the request paths that have the most slack, you can schedule with lower priority without impacting your overall end-to-end latency, and you can reduce latency times that way. And so they do that, they do the slack time analysis, and they do one more thing, which is identifying segments correlated with performance anomalies. So that's all pretty good, but it needs you to have this request identifier that goes across all the tiers. Before we move on to the solution for that, just a brief mention for Gorilla that you might be interested in. I'm not going to say much about this, but Gorilla is the in-memory time series database that Facebook use to record and store the 1 trillion monitoring data points that their systems generate every day, which is a pretty staggering number. And so again, it's a system where all the monitoring data comes in. It's kept in an in-memory database. It can hold 26 hours worth of data before the longer-term stuff is pushed out to HBase. And what's really interesting about that is that they can do a little bit of time series correlation. So if you've got a problem where there's some kind of anomaly, you can look and correlate with what else was going on at the same time that was also anomalous. So that's an interesting paper to study too, but back to our thread of understanding what's going on. Maybe you don't have a request identifier. Now what can you do? Well, all hope is not lost. There's a great piece of work called LPROF, which actually basically the idea is we'll make the most of whatever you've got. And so it's a non-intrusive request flow profiler, but the goal is the same, understand what the hell's going on. And so their view is the information in the logs, basically whatever you've got, is probably sufficiently rich to allow the recovering of this structure. And LPROF is a performance profiler, but you could use this recover structure for many things. So how does it work? Well, it requires access to the source code. And so what it does, and it's implemented for Java systems, does static analysis. It looks at your code, looks at all the logging statements, and it actually generates regular expressions to say, statements you see in the log could have been matched by this particular log statement in the source code. They look at the variable parameters in the log statements. They do analysis to see which ones actually get modified and which ones don't in the program flow, so they know which are candidate things to identify requests. They look at flow through the code to see that this statement always must come before that statement, etc. Bunch of tricks to try and figure out statically what's going on when you see the log to enable you to infer this request structure at the end of it. And what's pretty impressive is in the evaluation, which I think was HDFS, Yarn, Cassandra, and HBase from memory. They looked at a bunch of those kind of systems, real-world systems, looked at examples of real-world performance anomalies, and showed that actually in a high percentage of cases, with not doing anything special, they could accurately figure out what was going on and get to pinpointing the causes. Which is pretty good for a zero-touch system that you just give it your source code and say, go do an analysis for me, please. OK, last paper I'm going to talk about in this area, which kind of made me smile for two reasons. So one is it touches on something that certainly, having been a developer for many years, rings true, which is either it seems you've got way too much information in your log/trace and you're just drowning in a sea of irrelevance, or at the one point where you really wanted to know something, you don't have quite enough. Both of those things often seem to happen many, many times. And so pivot tracing is a system that says, well, yeah, that's going to happen. So why don't we just make it so that you can add and remove different instrumentation at runtime, which is not a new idea. I mean, it's very like what we used to do with AspectJ and the load time weaver back in the days, but it's a beautiful system built around it. It does do a very load time weaving kind of capability. There's a really elegant little query language that lets you say what you're interested in capturing, and it does a bunch of other smarts to pull information from the distributed system together. But really nice piece of work saying this is how we can actually tap in and get information that we didn't have up front. So that's the final piece in the armory. So we've talked about figuring out the big picture, getting an understanding at a high level of what's going on, seeing how requests flow from one to another. I want to talk a little bit now about when things actually concretely go wrong. So you've got a bug, so you know something bad is happening, but you don't know why. And in particular, I want to start by showing you this really great piece of work on something called failure sketching. Automated root cause diagnosis of in-production failures, which is a pretty cool thing if you could really pull it off. And so let me show you what the tool does, and then we'll talk about how it does it. And so, first of all, the challenge. The greatest challenge, why in production, is bugs that only occur in production and can't be reproduced in-house or on your laptop, which actually I spent most of Saturday wrestling with just one such bug that happened in production and not on my laptop. Diagnosing the root cause and fixing such bugs is truly hard. We're talking about kind of like there's a 100 machine cluster running. Once every 24 hours, this really weird thing happens, and I can't quite pin it down kind of bug, which is sort of the developer's worst nightmare. And what the failure sketching team do, there's a tool called GIST, and it produces GISTs of what caused the failure. And this is an example GIST. So you can see in this case, it was a real bug in Apache that they reproduced under their system to show you the kind of diagnostic you get. This is a double free bug, and there GIST shows you here's thread 1, here's thread 2. This is the flow. You can see where the 2 frees happened. What I particularly love about the paper that makes me smile is that the authors apologize at this point for the lines they've included in the GIST that here are in gray. And the reason they apologize is that, well, really, they're not part of the absolute minimal GIST, and we'd like them not to be there. But frankly, I'd take this kind of summary any day. Really valuable information. And they tried lots and lots of systems and were able to reproduce it. So very, very, very clever tool. So how does GIST basically work? You need 3 things. You need a stack trace or equivalent. This is where the problem actually was. So you know where, and in a sense what, like null pointer, etc., but you don't know why. You take the source code and you take a binary. And again, there's analysis of the source code that now happens once we've got the where to figure out what are all the possible causes of this problem. And then the runtime is instrumented. This is done in a really particularly neat way. Super low overhead and non-intrusive to your program. So they use a new feature in the Intel hardware called Intel Processor Trace to do it. And you need a modified kernel, but it's research. That's fine. Maybe you'll get this in your production systems in one day, but otherwise it's non-intrusive to your program. So they switch on this tracing now at all the places that are possible causes. And I'll say the overhead is astonishingly low, given the way that they're doing it. And it just sits there and watches. And it records all the non-failing normal runs. And when you get one or more failing runs, it's also going to capture them too. Once every 24 hours, it'll come around, it'll get it. And then basically it does a diff between the information it captured for the failing run and the information for the successful run, and produces these little GISTs. Very, very clever. It was evaluated using genuine failures from a number of different programs, real software, Apache, SQLite, Memcached, etc. This is impressive. Managed to build failure sketches with an average accuracy of 96% for all the failures. As you see, really, really low overhead. So wouldn't you just love in your production system, if there's a stack trace, for 96% of them, you automatically get this little GIST saying, oh, by the way, this is why. That would be beautiful. So this kind of thing really, bit of a game changer. Until you have that kind of capability in your deployed environment, there's some other research, a little bit older, but also really useful technique. Simplifying and isolating failure-inducing input, also known as delta debugging. So this is all about I've got some input that's causing my program to crash. And so the examples in the paper are maybe it's a web page that's crashing my browser. It was Mozilla at the time this paper was written. Maybe it's a program that's crashing my compiler, anything that takes textual input. So these days it might be like a JSON document or something that causes a crash when you receive it. And the challenge is often you've got some great big input. And one of the things that developers often spend a lot of time doing is trying to figure out, well, what is it amongst all of this that's really causing the failure, and getting it down to a minimal test case that just has the bits you need. It makes it much easier to solve the problem. And that's what delta debugging does. And it's pretty clever, and it's astonishing that it actually works. So take a C program like this C program, which once upon a time used to crash GCC. And so we know that this program will cause a bug. We don't know exactly what it is in this program that causes a bug. And you run it through this delta debugging minimization algorithm. It's called ddmin. And what you'll get back is something that looks like this. This is the minimal program from that input that will cause that bug. In fact, if you change any one character, or add or remove any one character here, the bug won't happen anymore, at least from the reducer trying to take it out. And so they're able to collapse that right down. It doesn't look particularly readable as a program, but what's really impressive is this algorithm knows absolutely nothing about what a valid C program is. They did the same thing with a web page that crashed a browser when it was printed and got it down to a single select statement. So it does this reduction, knowing nothing about what a valid C program is at all. It gets down to the smallest unit of change, which you can determine by input type. In this case, it's a character. Right? So we're going to get down to any single character will make this no longer fail. How it does it is kind of clever. And it's sort of a variation of a greedy binary search algorithm. So you start off with the failing input. If the failing input only contains one unit, in that case a single character, you're done. You can't possibly reduce it any further. If it doesn't, what you do is you just chop it in half, and you try each half. And maybe one of those halves actually reproduces the failure, maybe one of them doesn't. Quite likely, if it's a C program, neither of them work at all, because that's kind of what's happened at the first time. If you do get the failure reproduced in just one half, you reduce to that and you carry on. If you don't, you start this iterative process, just divide in half again. So now I've got 4 sections of the program. And we're going to try each one of those one by one. But we also try the complements. So if you look on that column, we've got I'll try the first quartile on its own, and I'll try the bottom 3 quartiles without the first quartile. And if one of those combinations reproduces a failure, we reduce to that and we keep going. If they don't, we divide again until we're getting down to individual character changes. And astonishingly, just this simple process can do that minimization we just described. Takes about 680, I think, might be 860, I can't remember in my head, iterations of that order to reduce that C program to the test case that we just saw. There's a variation called hierarchical delta debugging that exploits the fact that many of our program inputs actually have some kind of hierarchical structure. An HTML document, a JSON document, YAML file, XML, program code, whatever. They've all got this kind of tree structure to them. And it does the same basic algorithm, but it starts at the top level of the tree, and it does the minimization level by level in the tree. It turns out there's a tiny bit of knowledge. It's able to both give you better looking reduced programs and also do it much quicker. So instead of, let's call it 680, it can do it in 86 iterations, something like that. And with the HDD algorithm, my C program would start to look like this, which is a lot nicer. And so this is just a fantastic thing to have. If you think this looks interesting and you've got some nasty, horrible SOAP messages or something being sent to you that crash some awful financial system and you're in a pickle, it's about 150 lines of code in Python to write the thing that does this HDD algorithm. So it's really quite simple to reduce your test cases in this way. Very, very handy indeed. Now, Colin Scott et al. Took this kind of idea and said, let's take it to the world of distributed systems and try and minimize faulty executions across a complex distributed system. It's the same kind of principle, but applied at the next sort of level up. And so they work in 3 stages. First, let's assume that there's some sequence of external events that hit my system that cause a failure. We'll do this kind of minimization technique and something called dynamic partial order reduction to try and find the minimal causal sequence of the external events that actually trigger this failure. Once we've got that minimal external sequence, we'll then look at all the internal events that are happening inside my processes. They're working with ACA systems initially, so they're looking at all the little events and messages. And we'll try and minimize those. We'll keep the same external event schedule, and we'll try and reduce the internal events. And then at the 3rd stage, they say, well, now let's take the payloads that are coming in those external messages, and we'll use that kind of ddmin algorithm that we just looked at to try and minimize the payloads as well. So you get the smallest set of external events with the smallest possible payloads, the minimal internal work, that reproduces the failure in your complex distributed system, which is pretty cool when it's all put together. And they pulled the system together. Their motivation actually was that they were doing fuzz testing. And the fuzzer generates these huge unwieldy inputs that cause a crash, but like, well, is there something simpler? Now we know there's a problem here. And that's how they got into this whole game. And so we're looking at finding problems in Raft and in Spark, etc., using the technique. What's interesting here for me is these columns. So you've got number of events, external, and then the external in brackets there. And then look at the minimized column. So you're able to take, let's say towards the bottom in Spark, something that caused like 600 odd events in total to cause a failure when first detected, reduce that down to a sequence of 16 in about 15 seconds. So again, that's a pretty useful tool to have around if you've got this kind of complex, hard to debug problem. Okay, so that was looking at failures and how to reproduce them when you've got like a concrete, precise, like exception, error, etc. What about the more tricky things? We've hinted a little bit about it. So there's just like something's not performing quite like you'd like. It's a slowdown, and you don't quite understand why. There's no actual exception or failure. It's just sluggish. Why is that? And what can we do to help figure out why that might be the case? So we'll section why, oh, why. And the paper I really like in this area is called DB Sherlock. And what DB Sherlock does is it's basically an automated explainer for performance anomalies. And it's actually set in the context of database systems and integrated with an open source tool called DB Seer. But the technique could be used in a wide variety of settings, I believe. And so this is DB Sherlock. Very, very interesting system. And it's integrated in DB Seer. So DB Seer is collecting a variety of metrics from the database every second, just storing away those time series. And the starting point for an investigation is there's a slowdown. So it's not going to automatically tell you there's a slowdown, but there's a problem. You go in, you look in all these various time series, you see, look, this part of the graph seems to be where the problem is. And the interaction is you highlight this part of the graph and say, this is an abnormal region, or actually just this is a region of interest to me. Can you tell me, why is this different from the other stuff, i.e. what we'll call the normal execution? And that's kind of the setup. That's the challenge that you give to DB Sherlock. And what you'll get out of it is one of two things. You might get like a predicate-based answer. So in the top case, we say, look, there was a network slowdown ultimately, and these are the set of predicates that actually have the most explanatory power for why you saw poor performance there and not elsewhere. It's these things. The other nice thing they do is suppose you present the DBA, whoever it is, with this set of predicates, they say, actually, I recognize those things really mean that it was this higher order cause. And one of the examples in the paper is, actually this performance slowdown was caused by a rotation of the redo log file. And you say, right, now I'm going to associate this higher level cause with that set of predicates, and I'll add this causal model to my world. And when I'm looking at future problems, if I see a bunch of predicates that actually map one of my causal models with high confidence, I'll also suggest that as a possible explanation. So it kind of learns over time, which is kind of cool. So I really like the system. I thought to show you a little bit under the covers how it works. And so these are my sketches just grabbed and stuck on the slides. So we've got our time series, and we've got a normal region, things are going well, and our abnormal region that we're not so happy with. What we do is we find the low and high watermark for the ranges that we're covering, and we divide that up into a number of buckets or partitions. And just read across, and we mark each partition as, does this occur in the abnormal section or in a normal section? So we're marking them as normal or abnormal, and I think if there's a clash, the abnormal wins. I can't quite remember the rule, it might be the other way around. So we read across and we mark all the little partitions. If you bear with me, if we take that set of partitions we've got right there and you just mentally rotate it around like that for a minute, you'll end up with something like this, to the red, and you can just about see the green and the pink. So some of those cells are shaded in green, those are the normal regions. Some are pink, those are the abnormal regions. But it's pretty hard right now to really say, here's what differentiates normal from abnormal. So we go through a filtering and filling process. So what happens is, we look at each partition and we say, is my nearest non-empty neighbor on either side of the opposite kind? So if I'm a normal partition and I look and I've got an abnormal neighbor, That's aha. So I'm on some kind of boundary, and we just mark all those cells in the first pass, and we make them empty. What you end up with is this thing on the bottom, having you just about see the green, where we've got some green normal cells on the left, and some abnormal cells on the right, and a lot of gap between them. That's a typical thing you might find here. Not always, but maybe you will. Then we go in, and we do a filling process with some configurable bias towards things being normal, for example, that goes and fills in those gaps to try and find a boundary. And sometimes, for some time series, you'll find a nice clean boundary like this, or maybe the abnormal stuff is nicely segmented in the middle, where you can easily say, look, the average normal and average abnormal are separated by more than some threshold, and we can write a straightforward predicate. And if that happens, that's added to the set of predicates that can explain the problem. And that's basically how it works. We did a ton of experiments and show that this algorithm that on surface is quite straightforward is really effective in identifying correct explanations and much better than many state-of-the-art kind of expert systems and all other things. You see, it doesn't really have a lot of kind of intuitive knowledge about databases in here. And it's released as an open source module. It's in DBSeer. It'll be interesting to look at some of the kind of performance anomalies that DB Sherlock has been used to detect and correctly explain. And they cover the whole range of things that you may well expect to find and probably make you smile about what goes wrong in a database, from poor queries to poor physical design, CPU saturation, I/O saturation, slow networks, lock contention, you name it. It's used to give explanations that are really quite powerful in all of these different areas. So that's DB Sherlock, which I very much like. Now, we started this talk by discussing some of the need to close the loop a little bit between dev and ops and sort of why it's important that they work together. There's a paper, Runtime Metrics Meets Developer, that really takes this idea kind of to an interesting extreme. And it's actually very early work. At least it was at the time I read it, and I think it wasn't that long ago, so I'm presuming it still is fairly early. But I thought it was a very interesting idea. I wanted to share it with you today. And so, basically they're saying, look, a unifying theme, we've been talking about it, is a blurring of the boundary between building and operating software products. So in this paper, we explore what we consider to be the logical next step, which is basically they integrate monitoring data and other kinds of data, essentially, from production deployments into the software development environment that developers are using day to day. In other words, most people into the IDE. And they call this feedback-driven development. So kind of example, actually, if you go look at the paper on their website, they've got some screenshots of real IDEs, but I like this figure a little bit better just as an easy one to grasp. So you're working away in your code, and a bit like if you'd run a profiler locally and you might get some instrumentation showing up in the IDE about where the hotspots are, you'll get information about sort of what the profile, the behavior of this is in production of this kind of piece of code. You could equally imagine, for example, if you're automatically grabbing all those exceptions and errors, having something that's showing actually this goes wrong in production and flagging that kind of thing, etc. So really nice just closing the loop. I thought that was a really sort of fun idea. So that's runtime metric meets developer. At this point, so I would say we're nearly out of time, but we started a little bit early, so actually we do have a bit more time, but I've nearly used my half an hour at least, and so I thought I'd leave you with some timeless advice. And it comes from a great paper, actually written by a medical doctor called Richard Cook, but his advice is still very, very, very relevant to us today. And it's a little treatise on how complex systems fail. And he has lots of general rules, again, taken from sort of patient systems and operating theaters, but there's a lot of advice here we can translate into our world. Here's one really interesting thing that I picked up from that paper. The complexity of complex systems, that's sort of a tautology, makes it impossible for them to run without multiple flaws being present. Because those flaws are individually insufficient to cause a failure, they're regarded as a minor factor during operations. And so complex systems therefore run in a degraded mode as their normal mode of operation, which I think is also very true if you think about it when you get to systems of certain scale. That's a really good insight. And one other kind of thing he says is if you want to improve the operability of your systems and their stability, then this is what you want to aim for. He says you want to make it so that it's easy to discern where the edge of the envelope is between normal errors and sort of a pending catastrophe. So stuff is going wrong all the time, that's okay, But over here is the absolute catastrophe that's not okay. Where is that edge of the envelope? So you want to be able to discern that, and furthermore, for operators to understand how the actions they take either move the system towards or away from that edge. So there's really interesting high-level sort of insights in this paper. I hope you go away and have a look at it, and many of the others that I've talked about. So that pretty much completes our whirlwind tour. We've looked at the need to sort of bridge the gap between operations, design, and development. We've looked at some really interesting research on uncovering the big structure of your system and what's actually happening and how requests flow through it. We've talked about narrowing down the problems of failures, particularly with bugs, and getting automated sketches, explainers for performance anomalies, closing the feedback loop, etc. If you like that kind of thing, you hunger for more. This is a small advert. You'll probably like the morning paper. Again, it's the blog. It's on blog.colyer.org. I'll post the slides. I'm actually going to post pretty much the text of this talk, and all the links, etc., will be tomorrow's post. You can get an inbox subscription. Follow me on Twitter. That's where you can see the paper announcements, etc. If you're interested or want to take a photo, all the papers I mentioned from this talk are here, which hopefully on the big screen you can just about see. And again, I'll post this link for you so you can go back. If anything kind of caught your interest, I hope you'll go in and read it and start to discover a world of interesting things. So that's kind of just been a tour of cool things that are going on in research departments and in sort of large enterprises that perhaps haven't made their way out as fully into practice, but are really interesting and promising for the future. I was certainly pleasantly surprised how much there was that read onto operational issues. There were a whole ton more things I wanted to talk about that we didn't have time to talk about. So there's plenty in there, so I encourage you to dive in and get reading. So thank you very much.